We are discussing CSIR NET Physical Science June 2014 Problems of Quantum Mechanics. Here we are having 3.5 marks MCQ problem. Let us read the statement of this problem. Consider a system of two non-interacting identical fermions, each of mass m in infinite square well of potential width A. Take the potential inside the well to be 0 and ignore the spin. The composite wave function for the system with total energy is. We have to determine the wave function from the given energy. We have E is equals to 5 pi square h square by 2 ma square. The total energy of the two fermions in an infinite potential box is E n1 n2 p n1 square plus n2 square pi square h square by 2 ma square, equating this value to the given energy, that is 5 pi square h square by 2 ma square, implies n1 square plus n2 square is equals to 5, and this further imply n1 and n2 can take value 2, 1 and 1, 2. Thus, wave function of the particle, the wave function for the particle fermion must be antisymmetric. So, out of these two, 1 or 1, 2. So, if we look at to the option, they are given in terms of 1, 2. So, our option would be psi x1, x2 will be 2 by a sine pi x1 by a sine 2 pi x2 by a minus sine 2 pi x1 by a sine pi x2 by a. So, this would be our wave function. One might ask, sir, you haven't taken the value of n is equals to 2, 1. So, we just go to the action. Can you check it? 2, 1 with x? Obviously not. 1, 2, 1, 2. 1, 3 is not possible. 1, 1 is not possible. For 1, both these options are eliminated. Since wave function has to be antisymmetric, so then that would be our correct answer. A particle of mass m in a potential Vxy is equals to half m omega square 4x square plus y square is in an eigenstate of energy 5 by 2 h cross omega. The corresponding unnormalized eigenfunction of the system is, we have to determine unnormalized eigenfunction. Solution. We have V of xy is equals to 1 by 2 m omega square into 4x square plus y square, and energy of the particle is equals to 5 by 2 h cross omega. The Hamiltonian corresponding to this Hamiltonian that is h is equals to minus h square by twice m del square by del x square plus 1 by 2 m 2 omega square x square plus minus h square by twice m del square by del y square plus half m omega square y square, which can be written as hx plus hy. The wave function corresponding to this wave function corresponding to this Hamiltonian is psi xy equals to phi nx into phi ny of y. Further, phi nx will be defined as gamma 2 की power n factorial root pi की power 1 by 2 hn 2m omega by h cut x e की power minus m 2 omega x square by 2h cut, and similarly phi ny of y is defined as gamma 2 ny factorial root pi. Here it is x 1 by 2 h ny 2 m omega per minus m omega y square by 2h cut. So, substituting psi xy in this equation, we would be having it h applying wave function psi xy on Hamiltonian. We have h psi xy is equals to e nx into ny into psi xy, which give us implies e nx ny is equals to h psi xy divided by psi of x comma y, and this would result into e nx ny would give us h nx phi of x divided by phi of x plus h ny phi of y divided by phi of y, which is equals to e nx plus e ny, which is equals to nx plus half h cross 2 omega plus ny plus half h cross omega. So e nx into e ny turn out to be 2nx plus ny plus 3 by 2 h cross omega. But this term is equals to 5 by 2 h cross omega, implies nx would be 0 and ny would be equals to 1. Thus, the wave function corresponding to h psi xy is equals to phi of 1, phi of 0 x into phi 1 of x, which means we would be having it as, which means my phi 0 is m 2 omega naught, 2 omega by pi h cut की power 1 by 4 e की power minus m 2 omega x square by h cut into m omega pi h cut की power 1 by 4 into twice m omega की power h cut into y e की power minus m omega y square by h cut. So one can check it out. Our unnormalized wave function, this is a normalized wave function. Unnormalized is proportional to y e to the power minus m by h crowd coming out to be common omega 2x square plus y square. So if we check it out, our option A is correct answer. Here we would be having 2h cut, so 2h cut would turning out to be outside with negative sign. So our correct answer would be minus m omega 2h cut 2x square plus y square, option C. A particle of mass m in 3-dimension potential in 3 dimension is in the potential defined by this. Its ground state energy would be. So this is a spherical potential. We have to determine the ground state energy for this system. Solution. We have V of r is equals to 0. The radial equation for the particle moving in a central potential is given by 1 by r square divided by dr, r square dr by dr plus twice m by h cross square e minus vr minus l into l plus 1 by 2 mr square h cross square r of r equals to 0. Further, since Vr equals to 0, so our above equation reduces to d by dr r square dr of r by dr plus twice m h cross square e minus l into l plus 1 by twice m r square into h cross square r of r is equals to 0. Further, we define r of r is equals to u of r by r and take L is equals to 0 for ground state, electron in the ground state, for electron in ground state, in s orbit or ground state, s orbit we can write it down. So the radial equation becomes d square by u of r by dr square plus k square u of r equals to 0, where k square is defined as 2me by h cross square for r less than r. The solution of our equation is u of r is equals to a sin kr plus b cos kr. Further, applying boundary condition, ur is equals to 0 is equals to 0 and ur is equals to a is equals to 0. Now, so ur is equals to 0 implies a 0 plus b 1 equals to 0 implies b is equals to 0. So our wave function would be u of r is equals to a sin kr, and further second boundary condition, that is the u of r is equals to a implies a sin k equals to 0 implies k is equals to n pi and k is equals to n pi. K is equals to n pi by a, but we know it, k square is equals to twice me by h cross square, that is n square pi square by a square. So this implies E would be nothing but n square pi square h square by twice ma square En, and ground state energy would be pi square h square by 2 ma square. From here we can determine the normalization coefficient. The normalization coefficient radial wave function r of r will be radial wave function r of r is u of r divided by r, which gives us what? A by r sin kr. Normalization coefficient A is determined by r of r. R of r equals to 1 implies mod A square 1 by r square sin square kr r square dr 0 to a is equals to a square into a by 2 equals to 1 implies a equals to root 2 by a. Thus the normalized radial wave function is given by r of r would be a by 2 by a sin kr by r. Kr by r, and we can write it down as 2 by a 1 by r sin n pi r by a, substituting value of k, and its corresponding energy would be n square pi square h square by 2ma square, just similar to the particle in 1D box. Thus, our correct answer for this problem would be option A. Given that PR is equal to y h cross 1 by del r plus 1 by r, the uncertainty del PR in the ground state of hydrogen atom, wave function psi 0 r 1 by root pi a naught cube e to the power minus r by a is. So we have to determine the uncertainty of this problem. Solution: we have P of r equals to minus IH cross del by del r plus 1 by r into psi 0 r equals to 1 by root pi a cube e to the power minus r by a0. So let us determine the expectation value of momentum operator P is. Average P will be psi of psi 0 P of r psi 0 minus IH cross psi 0 minus 1 by a0 plus 1 by r into psi, which turn out to be minus IH cross minus a0 psi 0 psi 0 plus psi 0 1 by r psi 0 equals to minus 1 by h cross minus 1 by a0 plus 1 by a0 equals to 0, where we have used P of r psi 0 equals to minus I h cross del by del r plus 1 by r 1 by root pi a0 cube e to the power minus r by a0, which can be written as minus IH cross minus 1 by a naught plus 1 by r e to the power minus r by a naught by root pi a0 cube, which can be written as minus IH cross minus 1 by a naught plus 1 by r psi 0. Similarly, and the value of psi 0 1 by r psi 0 is always equals to 1 by a0. The expectation value of P square r square is obtained in the following manner. Applying the operator PR square on the wave function, PR square psi 0 equals to minus h cross square 1 by r d square r psi by dr square equals to minus h cross square 1 by r minus 2 by a naught plus r by a naught square into psi. 0, which can be written as minus h cross square minus 2 by a naught 1 by r minus 1 by a naught square psi 0. So, applying bra of psi naught on above equation, we get del p r square is equals to minus psi 0 minus h square into minus 2 by a 1 by r minus 1 by a 0 square of psi 0. So, this can be written as, here this term would be positive. Now this can be further modified as PR square equals to h cross square psi 0 2 by a0 1 by r minus 1 by a0 square of psi 0. This can be written as h cross square 2 by a0 psi 0 1 by r into psi 0 minus 1 by a naught square to psi 0 into psi 0. So from here we would be having h square by twice a naught into 1 by a naught minus 1 by a0 square, which give us h square by a0 square. Take the uncertainty. And the momentum defined as del PR is equals to expectation value PR square minus square, that is square by a square minus 0 equals to h cross a0. Now the question is, do we need to go through this detailed derivation in exam? So I would suggest obviously not. We would be using direct relation. Direct relation for determining uncertainty in delta PR or hydrogen like atom. And that relation is delta PR will be Z and H cross by A naught root over 1 minus 2L L plus 1 divided by N into 2L plus 1 for psi 100. Del PR will be for hydrogen atom 1 H cross A by A naught root over 1 minus 2 0 into 0 plus 1 divided by 1 into 2 into 0 plus 1. So we would get H cross A naught. So in both the cases, the answer is turned out to be H cross by A naught. Thus our correct answer would be H cross by A naught, option A. The ground strength eigenfunction for the potential Vx is equals to minus delta x, where delta x is delta function is given by psi x is equals to a e to the power minus alpha. where A and alpha are constant. If the perturbation Bx² is applied, the first order correction to the energy of ground state will be. Solution. We have psi of x is equals to A minus alpha mod x, where h dash is equals to Bx square. The first order correction in the energy. The energy is given by E11 would be psi h dash psi divided by psi dot psi. This denominator term we are taking because this wave function is not normalized. Had the wave function is normalized, then we would not take it this value as 1. So we would be having psi conjugate star x h dash psi of x dx divided by psi conjugate star x into psi of x dx. Substituting the value of wave function, so the E1, 1 would become twice a square 0 to infinity e की power minus twice alpha x bx square dx. In the denominator we would be having twice a square 0 to infinity e की power minus 2 alpha x dx. The value of this term would be 2 divided by 2 alpha cube 2 factorial, and in the denominator it would be 1 by 2 alpha. So here we would be having it b into 2 alpha into 2 divided by 2 alpha cube, which turn out to be b by 2 alpha square. Thus our answer for this problem would be option D, b by 2 alpha square. An electron is in a ground state of hydrogen atom. The probability that it is within the Bohr radius is approximately equal to. So we have to determine the probability of the electron inside the Bohr radius. Solution. The wave function of an electron in the ground state of a hydrogen atom is psi r equals to 1 by root pi a0 cube e की power minus r by a0. The probability of finding the electron within the Bohr radius is PR less than equal to A naught equals to 0 to A naught psi star psi d tau, that is equals to 1 by pi a0 cube 0 to a0 e की power minus 2r by a naught pi 4 pi r square dr, which is turned out to be 4 by a naught cube 0 to a 0 r square e की power minus 2r by a naught dr. So this would turn out to be 4 by a naught cube by 4 minus 5 plus e square divided by e square. And when we solve this value, this is turned out to 0.323. So probability of founding the electron outside the Bohr radius would be 1 minus 0.323. So this value for outside would be roughly 0.68 something. Okay. For this problem, our correct answer is option D. A particle in the infinite square well, where potential is defined as Vx is 0 in the range 0 x less than a and infinity otherwise, is prepared in a state with wave function a sin cube pi x by a in the region 0 x a and 0 otherwise. The expectation value of energy of the particle is, we have to determine the expectation value of this particle. So solution, we have V of x is equals to 0 infinity 0 x less than a otherwise, and its corresponding wave function psi of x is equals to a sin cube pi x by a. Now the normalization constant a is obtained from normalization condition, that is psi dot psi, inner product of psi dot psi must be equals to 1, a square 0 to a sin 6 pi x by a dx is equals to 1 implies a square is equals to 5a by 16 equals to 1 implies a is equals to root 16 by 5a. The normalized wave function is given by psi of x is equals to root 16 by 5a sin cube pi x by a. The Hamiltonian for such a potential is h is equals to minus h square by twice m d square by dx square. The expectation value of energy is E is equals to psi h psi equals to 0 to a psi star h psi dx, which is equals to 16 by 5a cube, a 0 to a sin cube pi x by a minus h square by twice m d square by dx square sine cube pi x by a dx. So this become minus h square by twice m 3 pi square by a square 16 by 5a 0 to a sine cube pi x by a 2 sine pi x by a minus 3 sine cube pi x by a dx, which equals to minus h cross by twice m 3 pi square by a square 16 by 5a 2 0 to a sine 4 pi x by a dx minus 3 0 to a sine 6 pi x by a dx, which is equals to h square by twice m h square by twice m 3 pi square a square 16 by 5a 2 into 3a by 8 minus 3 into 5a by 16 minus this will turn out to be 9 h square pi square by 10 ma square, where we have used I1 is equals to 0 to a sine 4 pi x by a dx is equals to 3a by 8 and I2 equals to 0 to a sine 6 pi x by a dx equals to 5a by 16. Thus, our answer for this problem is option C. This scattering amplitude f theta for the potential VR equals to beta e to the power minus mu r, where beta and mu are positive constants, is given by Born approximation. By in the following, b is equals to 2k sin theta by 2 is equals to h square k square by 2m. So we have to determine scattering amplitude f theta. Solution: we have P of r is equals to beta e to the power minus mu r. Since potential spherically symmetric, therefore the scattering amplitude of the particle f of theta is equals to minus 2 mu h square q 0 to infinity r dash v r dash sin q r dash dr dash, where q is equals to 2k sin theta by 2 and k square is equals to 2 mu e by h square, and theta is scattering angle. Substituting the value of VR in F theta, we get F theta is equals to minus 2. In the question it is given in terms of M, so I would be replacing my M here. Otherwise there would be confusion. M minus 2M beta H square B. In the question again, it is B, which is defined as 2k by sin theta, so in denominator this term would be replaced by B. So H square B R dash sin B R dash e की power minus mu R d R dash 0 to infinity, and this term will be equals to minus 4m beta mu divided by h cross square b square plus mu square का whole square, where we have used the value of standard integral, that is r sin br e की power minus mu r dr 0 to infinity is equals to 2 mu b square plus mu square का whole square. So our correct answer for this question is minus 4 m beta mu, option A, h square beta square mu square plus.